Any question? Yes, Joseph.
What's the symbol next to J on the negative H prime?
There's nothing. It was
Bracket.
collection. Yeah, it's not. So this is the Lagrange multiplier. Well, why do you call it Lagrange multiplier? Because Lagrange found it. Why is the multiplier? Because of the following. Okay, so nabla f equal c times nabla epsilon. Get nabla epsilon to the left-hand side, and they will have this thing, which is nabla all over f minus c epsilon is 0. Oh, so it's not the gradient of my function that is equal 0. It's the gradient of other modified function. This modified function you can expect it's called the Lagrangian. It's simply your objective plus some constant, called the Lagrange multiplier, times your constant. So, what is the Lagrange multiplier rule? I'm given a function f that I want to minimize subject to some constraint. If it's an unconstrained problem, simply get the nabla f equal to 0, right? If it's a constrained problem, it's not nabla f equals 0 anymore, but nabla something else. What's this something else? It's f plus lambda times your constraint. Nabla of the L is the 0 thing that you're looking for. This is the Lagrange multiplier, okay? And we're going to talk about it more now. We're going to apply it into a problem and solve it actually geometrically to show you more what's this geometrical meaning. Yes, Mikael?
So how we find lambda?
It's an unknown, the Lagrange multiplier. You tell me, in the unconstrained problem, unconstrained, f, x, and y, how many equations and how many unknowns do we have? How many equations and how many unknowns?
Two equations, two unknowns.
We have two equations, two unknowns. What are the two equations? Is the nabla f equals 0 give you two equations, it's a function of two variables. And the two unknowns are the design variables, x and y, three variables, right? If it's a constrained thing, then how many unknowns do I have?
3.
X, y, and lambda. And how many equations?
3.
3. What are the 3? It's 2 from here, partial L, partial x equals 0, partial L, partial y equals 0, and constraint. Okay? We're going to do it now. We're going to do an example in detail, but let's do this first. So then another example. It's minimization of a function here, f of x and y, x squared plus y squared over x and y, subject to a constraint y, subject to y should be equal 1 plus x squared. Okay? I can apply this rule and solve it, get 3 equations, 3 unknowns and solve it, but I'll do it in a different way. I'll do it graphically to show you the meaning, the geometrical meaning of the Lagrange multiplier. Any questions so far? Any questions? Yes, Anshul?
Does this hold only for continuous functions? If you had a singularity in the range of x and y, would that still hold?
Yes. This whole branch of science, because it is dependent from the beginning on differentiation. The function should not only be continuous, but differentiable. Okay? At the optimum point. If your function is not continuous, then do something else. There's another branch of science called the global-based optimization. This is what we call gradient-based optimization. You can tell why, because it's based on gradient and differentiation. If your functions are not smooth enough, don't do gradient-based. Like the genetic algorithm, for example, GA command in MATLAB, does not require smooth functions. Okay? At any rate, I love gradient-based, so let's go to the gradient-based. This is the science here, because you have a mathematical condition for termination. What's that? The derivative equals 0. Over there is no mathematical condition for termination whatsoever. If you keep searching, you will always find it. Okay? At any rate, so I have this problem and I want to solve it. So like I said, my x and y in the branch of optimization, we call them design variables. I want to design x and y. Sometimes they are also called free variables. Okay? So sometimes we love to draw what we call the design space, right? X and y, and I'm looking in this x and y for the optimum point. Then we draw contours of my function. What do you mean by a contour? Well, what is the set of points over which f is equal to 1, for example? Equate f equals 1, right? So gives you x squared plus y squared equal to 1. What's this equation? Circle, it's radius 1, right? Or let's start by 4. Then here is a circle of radius 2, for example. Every point in the circle, the objective function f has a value of 4. Okay? Okay? Every point on the circle has the same value of objective function. Then you reduce it further, reduce the objective function. The objective function is simply the radius squared, right, in this example. So there's another smaller objective function, smaller objective function. So if I want to minimize this, subject to no constraints, unconstrained, what is the global optimum?
0.
The origin. Okay? Any question about that? Now I have a constraint, so to make the problem a bit more interesting. Let's plot that constraint. It's 1, maybe this is 1, plus x squared, so it's a quadratic function of x, something like this. So I'm telling you, no, please don't give me nabla f equals 0, the unconstrained, because it's here, it simply doesn't lie on my constraint. Your point, optimum point, has to satisfy this constraint, has to lie on that curve, okay? How to do it? Well, here is a point that lies on your curve, but it's not the best. I can do better by reducing my radius. I can get here, for example. Well, I can do better and better. Until what?
Until it gets.
Until it doesn't get there.
Yes. So, how do you describe it? Until what? I'm reducing my radius until what?
Until it stops
Until
touching
the
1.
stop is 0 there.
You just touch it, right? Until you just touch it, correct? And how do you describe just touch it in a mathematical term?
Tangent.
Not very complicated.
Tangent.
They have the same tangent, that's correct. How do you describe the same tangent?
One solution.
Different.
What about the same tangent implies the same normal, right? This is the normal of the red. It's in that direction. And this is the normal of the green. It's again in that direction or the reverse direction, doesn't matter, right? They are what? They are parallel. This is the Lagrange multiplier rule, right? Is that the gradient, the normal of your function, is parallel to the normal of your constraint, correct? This is the Lagrange multiplier rule, which means from here, how do you proceed? To prove the thing, nabla f equals the constant multiple times nabla f psi. Get them together, like here, and you have the nabla of your Lagrange inequality, right? Any questions so far? Any question, please? So this is pretty much 2/6. There's nothing more except the technicalities, because the inequality constraints. So far we have been dealing with equality constraints, right? Y equals h of x or something. Or if psi of x and y equal 0, not less than or equal 0. You know how we do inequality constraints? There's nothing behind it. We simply try it both ways. So actually this constraint was like this. Greater than or equal. But if you know the physics of the problem well, you can turn any inequality constraint into an equality constraint. First, how we solve inequality constraints? If psi of x and y is not equal to 0, is less than or equal to 0, or greater than or equal to 0. We try both cases. Strictly less than, okay? So we solve the problem without the constraint at all, ignoring the constraint, as if this constraint does not affect the problem. We call it inactive constraint. It's not, as if it's not there. And we get the optimal solution, we check the constraint. Is it satisfied or not? If it's satisfied, I'm done. If it's not, this means what? Your constraint will be active, will be exactly equal. Okay? So here, it's greater than or equal. I solve the unconstrained problem, and here is the optimal. Is your constraint is satisfied? What's
No.
your constraint? Is that my y is greater than this guy. So actually my constraint is that I have to be above this line. I cannot be below that curve, right? Cannot be below. I can be above, only above. On the line or above. I solved the unconstrained, I found it here. It's not satisfying the constraint. So the best you can do is that you are exactly on the line. So you solve it once, unconstrained. If it's not satisfied, then you do it, you convert your constraint into an equality constraint. This is what we call the switching condition. This is the logic behind what you call the switching condition in the optimization. We don't need all these technicalities here in this course. But I need this. I need the Lagrange multiplier rule. I need you to understand the Lagrange multiplier rule. Yes, Mikael.
So how do we apply this in dynamics?
Yes, it's very good. What the hell this has to do with dynamics? Right? What the hell this has to do with dynamics? It's still a long story to tell. We'll not answer this question today, but I'll give you just a hint.